the PLT. Okay. So yesterday we started the topic of HTTP, and this was exactly where we left yesterday. Okay. We discussed the basics of HTTP. Okay. We saw that there are two different flavors or versions of HTTP. HTTP 1.0, which is the non-persistent HTTP, and HTTP 1.1, which is the persistent HTTP. And the basic difference between these two flavors was that the HTTP 1.0, the non-persistent one, was the one in which we have at most one object sent over a TCP connection, and then the connection is closed. And we saw, with the help of an example, we discussed that the performance is of this sort of HTTP, of this version of HTTP is quite poor. So the page load time is quite poor. And then the improvement came in which we started having a persistent TCP connection, and then all the objects of the web page can be retrieved through that TCP connection. Okay. But please remember a very important thing, that for both the flavors, for both the versions, for the persistent HTTP and for the non-persistent HTTP, for 1.0 or 1.1, and even the one which we will discuss today, 1.1p, 1.1 with pipelining. So HTTP 1.1, which is both persistent and pipelined. Okay, we will discuss it shortly in today's lecture. Please note that in all the flavors, for each the difference is the TCP connection. Okay, the TCP connection will stay persistent, but there will be separate request and response for each HTTP. There will be separate HTTP request and response for each web object. Okay, just give me 10 seconds. I'm sitting in CR5. There is no one in front of me, but I thought maybe there will be some students in the FTF mod. So I'm sitting in CR5. I need to close the door so that the disturbing voice coming from the other room should be a bit lower. Just give me 10 seconds, okay? Right, Ji, I'm back. Sorry, the CR6 is in front of CR5, and CR6 it was on the speaker. So okay, right, back to what I was discussing. Yes, so in all three versions, please remember, there will be separate request and response messages exchange for each web object. Okay, even today, even in HTTP 2.0 in Google's PD. So if a web page consists of 50 web objects, 50 different web objects, so there are, let's say, 20 images, 10 Java applets, and there are base HTML file, and there is tables and CSS style sheets. In total, 50 web objects are there to display a web page. Please note, in each and every version of HTTP, 50 separate request and response messages are exchanged. Okay, 50 separate. Although HTTP 2.0, the Google's PD, which is the very latest version, and our browsers support that version, it sometimes multiplex some of the requests. Okay, but in any case, all versions have the same limitation, that a separate web object request, separate request and response message is required. So the persistent does not mean that in a single query every web object is being requested. No, persistent means that the TCP connection will stay persistent, okay? And then in that persistent connection, there will be HTTP request for each web object, and then for the second web object, and then third, and then the responses, and then the web page will be rendered in totality, okay? So we discussed all these things, and then we discussed that we discussed the other concepts of HTTP, including its header structure, the header structure of request message, and the header structure of the response message, and we saw it in Wireshark as well, and also we discussed the concept of cookies. So moving on, we started discussing the PLT, and this was the slide where we left, and we discussed the first option in great detail, and I also showed displayed, I mean demonstrated the ping DOM test in front of you guys of our own website, www.nust.edu.pk, and we saw that a good fair amount of portion of the web page is comprised of the static images. So it is very important in the way the images are designed, and what sort of images are used, which .tiff, .jpg, .png, whatever, okay, or how they are being rendered, and things like that. So all of these things comes under this point, and all these things are related to a better web page design. But today we will discuss the techniques of improving PLT, which are mostly related to networking. Okay, so let's start. The first technique is changing HTTP to make better use of the available bandwidth, and this technique requires the use of the 3Ps. Okay, so the 3Ps are basically persistence, pipelining. These two P's are important and famous and mostly used. And the third P is parallelism, but it is not used very often. So sorry about my writing, but three P's. So you can because HTTP is the protocol at the heart of the World Wide Web. If you improve HTTP, you will definitely improve the page load time. Okay, so if using the three P's, using these three techniques of persistent use of having persistent HTTP, pipelined HTTP, and parallel connections will definitely improve the performance of the protocol, and as a result, reduce the page load time. So let's see how it will be achieved. Before that, this was the problem with HTTP 1.0. We can see that we spent some time in the setup of connection, okay, and after setting up connection, and during this we exchanged two messages. So there is one RTT involved during this time, the setup of connection, and then we request the web object, and then the response come, and this gray area represent the transmission time of the web object. So we can assume that there will be because the connection setup and because the HTTP GET request, these are very small in size, just few bytes. So we can ignore the transmission time of these all these three packets or three messages, but we should consider the transmission time of the actual HTTP response, in which we have the data coming as well. So basically the web object. Actually, this is how the first object is going to be retrieved, and then the connection setup, and then the second object is requested, and then the transmission time, and then connection setup again, and up to so on. So this was obviously 1.0 non-persistent, fairly poor PLT, and things like that. We can have two scenarios. We can have multiple TCP connection set up to same server if the objects are all placed on the same server. And let's not go into the detail of this thing right now. I will explain this later. Okay, because it is in modern day internet, it is quite possible that you want to retrieve a web page, and some of the objects of the web page are placed on one server, and some other objects of the web page are placed on some other server, or maybe dispersed or distributed among many servers. So in that case, you will have to establish separate TCP connections with all the servers. Okay, I hope you are understanding what I'm trying to convey here. Okay, so it is possible that a web page that a web page to display the web objects of all to fetch the web objects of that whole web page and to display that web page properly, it is possible that the web objects are distributed among many servers. They are not on the same server. Okay, in that case, whether it is non-persistent TCP or it is whether it is non-persistent HTTP or it is persistent HTTP 1.0 or 1.1, you still have to maintain separate TCP connection with each and every server. Okay, I will discuss this in a little bit in more detail later on. Okay, so how to improve PLT? We have persistence, we have pipelining, and we have parallelism. But parallelism is not a very famous P. We generally do not use it because browsers can run multiple parallel HTTP connections, HTTP instances, but the parallel connection will compete with each other for the network resources. For example, if you are browsing some website and your browser supports parallel connections with the same server, and it established, let's say, 8 parallel connections. Most browsers support up to 8 parallel connections. Then these parallel connections will be competing with each other for the same network bandwidth. So for instance, right now in this PC, if I open up the browser and I surf the web, and the browser uses parallel connections. Okay. So I was discussing what? Yes. So the parallel connections, they will compete with each other. Okay, for the network resources. So first we will discuss the other two P's. This is a very all important slide, and please pay very close attention to the explanation of this slide. We have 3 different versions of HTTP, and these are the time sequence diagrams. Okay, so the time sequence diagram of HTTP 1.0 over here. Okay, HTTP. Let me not write HTTP again and again. Let me just write the version. And this we have over here is version 1.0, and we have over here is version 1.1, and over here is version 1.1p. Okay, so pipelining is being used here. Okay, so 1.1 is persistent. Okay, 1.1 is persistent, but 1.1 this 1.1 is both persistent and pipelined. So you can see on the diagram that because this is the time sequence diagram, so we can see that the soon the transmission is finished and the web page is being rendered, the better is the performance. So you can from naked eye, the first thing that we can see immediately is that okay, here the transmission finishes up until here, and here the transmission finishes a bit early, and here it finishes a bit early. So these are the time sequence diagrams, time run from top to bottom, and what we want to do is we want to achieve the same result in lesser amount of time, because this page will have that much amount of PLT. This is the PLT. Okay, this is the PLT. Then this one has this PLT. Okay, this is the PLT, and then this one has, this is the page load time. Okay, so we can see a steady improvement from 1.0 to 1.1 persistent and 1.1 persistent and pipeline both. Now let's see why is this happening. So one difference is very clear. It's quite simple. In 1.0 we are setting up connection again and again, and in each connection we can only retrieve one web object. And in 1.1 we don't have to do this. So we set up the connection just once, and then after that we request the first web object, and when the web object is received, let's say it's the base HTML file, we started parsing the web object, and then after parsing the web object, the base HTML file, we start requesting for other we see in the file that there are other references to the other web objects, so we started requesting those web objects as well. Okay, let's stay with these two. Okay, so we can clearly see that the connection setup time is removed over here. Okay, and please note one more thing is that the white areas. Yes.
Sir, can you please slow down?
All right. Okay. So the white areas, they represent no usage or limited usage of the network, and the gray area, this represent proper use of the network. So what we want to do is that we want to minimize the white areas in the diagram. Okay. So you may notice that uh, I mean the white area is means that the network bandwidth is not used very efficiently, because there was a TCP connection request of very few bytes, and then TCP connection response of very few bytes, and then the HTTP GET request of again a very small one, and then here we use the network by transmitting a large web object. Okay, and then again a white area, and then some use of the. So we want to maximize the gray area. That means that the network usage is being maximized. Okay. So you note here that we are trying to limit the white area over here, because the connection setup time is removed. So the white area is only for the half RTT when the request of the next web object reaches the server, and when the server receives this next request, then it respond with the web object. Okay, so these are sequential requests. Now we can do one more improvement. Okay, this is HTTP 1.1 persistent, not pipeline. This is persistent, not pipelined. Okay, now we can do one more improvement, and that improvement is that instead of these sequential requests, we can ask the web objects in a pipeline manner. What does that mean? Okay, so again, connection setup, request for the first web object, which is the base HTML file. The base HTML file is being received over here, and as soon as the client started parsing the file, and the client noticed that there are other referenced web objects in this file, the client started requesting for those web objects, but this time in a pipeline manner. Okay, this time in a pipeline manner, not in a sequential manner. So you notice that over here, as soon as it started passing the base HTML file, it started requesting the web objects in a pipeline manner. Okay, so you can see the file transmission has not finished up till yet, but the second GET request and the third GET request are being sent back to back. What benefit will it bring? Okay, now if you notice that the white areas are further reduced in this version, and the reason is, in the case of sequential request, when the whole web object is being received, then the client request for the next web object. Now this half RTT is totally a time in which this request is being reached from client to the server end, and this is the time when the network usage is really very minimum. Okay, so I mean the network is not used to its proper capacity, and then when the server receives, then it starts transmitting the web object. So what the pipelining bring to the table is that these white areas are further reduced. Okay, with the help of pipeline request, as soon as the server started finishing the previous web object, it already has a next request, and instead of waiting for half RTT for the next request to arrive at its end, it immediately serves the next request and send the next object, and then the very next object, and up to so on. Okay, so we notice that the gray areas.
Sir, please you repeat करते हैं pipeline.
Okay, so the main difference between between HTTP 1.1 persistent and HTTP 1.1 persistent and pipelined. Okay, the main difference is that in this version, the requests will be from the client to the server will be received in a sequential manner. In a sequential manner means that the client, after fully receiving the previous object, will request for the next object, and due to this phenomena, there will be a waiting time of half RTT. Okay, when the request will leave the client and reaches the server end, and then the server receives the request, and then it will transmit the object, and after receiving the object again fully, I mean the client knows after parsing the file that this file contain references to two more objects. So why not just request those objects in a back-to-back manner? Okay, so send one request, okay, send another request. Now again, to the very beginning of my lecture, I told you guys that in each and every HTTP version, there will be a separate HTTP request for each web object. So it is there, okay, but it is there in the with a separate connection. It is there with just single connection in a sequential manner, and it is there with a single connection in a pipeline manner. Okay, so we establish a connection, we receive the base HTML file, we notice that there are two more reference objects. Now instead of waiting for the whole file to be received, we as soon as we encountered that there is a reference to another web object and I need that web object to render the page correctly, I let me just immediately send the request. Okay, and then the next web object, let me just immediately send the request. In this way, while the server is transmitting the previous web object, there is the next request is on its way to the server. And when the server, as soon as the server finishes transmitting the previous web object, it will serve the next request, and then immediately the request after that. Okay, but in this case, the server, after serving the request, will wait for the client, because the client will send the request in a sequential manner. Okay, first object received, request for second object received, request for third object received. Okay, now I will render the web page. Okay, not in the case of pipeline. Okay, I hope it is clear now.
Okay, sir.
So these are,
Thank you.
yeah.
Yes.
Sir, in sequential, like the client is basically maybe arranging its request, like which requests are same, and it should request to the server at
No,
the same
no,
time.
it's not like that. It's not like that. This is just a over the air improvement in the protocol. The HTTP at the very beginning of its advent, when the World Wide Web started, early 90s, it was like this. Very poor PLT, but soon as the internet started to expand, it was realized very soon that this will not, this is not going to work out. And the people, they started having a persistent connection. Okay, but then they soon realized that okay, persistent connection with sequential request can be further improved by doing this. So it's just the way HTTP grows or improved over the years. Okay, okay.
Okay. Okay.
Over the year improvement hai. I mean, you realize that no, it can, this is the protocol at the heart of World Wide Web. Okay, even people are now doing research and now working in the direction of improving further HTTP. So after 1.1 pipeline, 1.1 pipeline stayed in the internet for a very long period of time, a good 20 years. Okay, it was up until just few years ago, 5 years ago, that Google's speedy start, HTTP 2.0 start to become part of the browsers. The browsers started supporting, and still there are some of the features of Google Speedy which are not very mature and very how do you say, very properly tested. Okay, so 1.1 persistent was there since from 95 to 2015, maybe a good period of 20 years. Okay, so this was the one which we kept using for browsing our internet. Okay, so HTTP improving HTTP is always a need, and they are always thinking of new ways to improve HTTP. Okay, if you notice, when we do the ping dom test, we were greeted with few suggestions from the website, that the NUST website administrator should improve these things. Okay, so it's always there. Okay, so I have explained everything in this slide, but there is one more thing, and this is the question that I would like to ask to you guys. If you guys notice on the slide that the gray portion is of, I mean, we are taking an example of a web page which has a base HTML file and reference to two more web objects. Okay, a base HTML file and reference to two more web objects. Now, if you notice, I mean, the web page, it has, it has the base HTML file. Okay, base base file, and in this base file, let's say there are two images. Okay, that's it. That's the web page. I mean, the size of image is the same. Then why 1.0 is taking more time to transmit the same image, and 1.1 persistent and 1.1 persistent and pipelined is taking less time to transmit? I mean, this is the file transmission time. More gray area is shown over here, and less gray area is shown over here. Can you comment on that, anyone? Why the images of, it's the same web page, the base HTML file is same, the images are same. We are using three different scenarios. In first scenario, we are using 1.0 to render this web page. In the second scenario, we are using 1.1 sequential, and in the third scenario, we're using 1.1 pipeline to render the same page. It's the same size of base HTML file, the same size of first image, the same size of the second image. Why the base HTML file is rendered in the same time in all three versions, but the images are rendered in more time, retrieved, sorry, not rendered. The images are retrieved in more time in the 1.0 version and in less time in the 1.1 and 1.1 pipeline. Anyone?
Sir, is it because of bandwidth?
Okay, I should give the answer directly because because you guys don't know the reason right now. Okay, we have not discussed it. The reason is because of TCP, the way TCP operate. Okay, and if you notice, I skipped one point when I was discussing HTTP 1.0 in this slide. I skipped one point, and this point is over here. Okay, multiple TCP slow start phases. More in the lecture on TCP, more a couple of weeks later we will discuss more about it. But just to explain this phenomena, let me just allow me to explain this over here. Okay, I have some white space over here. Let me try to use this white space and explain you guys. Okay, so let's assume let me illustrate the behavior of a TCP connection. Okay, and we will discuss this in chapter 3 when we discuss TCP. But just to explain this question, the answer of this question that I just asked you guys, let me illustrate the behavior of TCP. So TCP, it is a protocol, and if you remember, I discussed the service model of TCP and UDP both, and I discussed that applications, they require data integrity, they require they require the delay, throughput, and security. And then we discussed that there are two service models. There's a dichotomy at the transport layer. We have TCP, which is a full fledged protocol, and we have UDP. If you remember, this was the first lecture of chapter 2. Okay, and we discussed that TCP, it performs reliable data transfer, it performs process-to-process communication, it performs congestion control and flow control, while UDP, it only performs process-to-process communication and nothing else. So TCP perform congestion control. Congestion control means TCP control the rate of sender in favor of the network. So TCP try to go slow on the network. TCP try to make sure that the network is not overwhelmed by the rate at which the sender is sending the packets. How TCP do this? The detail will come in the later chapter, but right now let me just elaborate how TCP work. TCP start very slowly. So what TCP do is that let's say this is RTT, round trip time, and this is the windows, this is how do you say, this is the not window size you have not discussed right now, the window size. This is the number of packets. This is the number of packets on the y-axis. Okay, so on the x-axis, the round trip time, the first RTT, the second RTT, the third RTT, fourth, fifth, sixth, seventh, eighth, up till so on. And on the y-axis, we have the number of packets. So how TCP start? TCP makes a slow start. Okay, slow start means that because right now TCP connection do not know what is the capability of the network, because the network is not visible to the TCP. I am using my laptop over here. I cannot see all the links and their capacity and their condition and the queue at the router. I cannot see it right now. Okay, so this machine, my PC, it will start the connection very slowly. It will send one packet in the first RTT, and then because it is starting from a very low rate, it will keep doubling the packets. So one packet, then two packets, then four packets, then eight packets, then 16 packets, and then 32 packets are up to so on. This is called TCP slow start. Okay, it is called slow start because it starts from a very low value. Okay, although it keeps doubling its rate, the increase is exponential, but generally TCP start very slowly. Slowly means not the increase is exponential: 2, 4, 8, 16, 32, 64, 128 packets. So you see, so in the 7th RTT, it will be sending 128 packets. In the 8th RTT, it will be sending 256 packets until the network starts shouting, until the network gives a message to the TCP that no, this is a bit overwhelming for me. And we will discuss the detail in the later lectures that how the network can give this message to the TCP. But for the time being, just understand what I'm saying, that the TCP starts slowly, okay, like this, and then the TCP move to the linear phase and increase the number of packets one by one. So 256, then 257, 258, 259, every RTT just the increase of one. So this phase is called the slow start phase. This phase is called the congestion avoidance phase. Okay, no more than this. No more than this.
Sir?
Let me conclude and then please ask the question. Okay, please बताइए. Please ask.
I just wanted to ask how is this different from TCP windowing?
TCP windowing? Can you
Yes.
please? Okay. Okay, Abdullah.
How is it different from TCP windowing?
Okay, Abdullah, this is not different than TCP windowing. I am just trying to camouflage few terms because I have not taught the lectures on TCP yet. So I want to communicate the answer to this question, which I just asked to you guys, but I want to communicate it with proper reasoning, and for that I am trying to give as little but as necessary information as possible from the TCP lectures, which will come a few after a few lectures down the line. Okay, so this is exactly the same as TCP windowing. You can assume that on the y-axis it is not the number of packets, but it's the window size actually. But just trying to camouflage few technical terms which the students don't know right now. Okay, I'm just do you get my the
Yeah,
notion?
sure.
Okay.
Yes, yes. Yeah.
This is exactly the way TCP windowing works. This is exactly TCP windowing work in the slow start phase and then in the congestion avoidance phase. We will study that in detail. But because right now the students do not know the window size of the TCP, I'm just trying to camouflage complex details with the easy words, and I'm just trying to tell them how TCP start its connection. So TCP start very slowly. Now, if I ask you guys again, why are there why is there more time required to transmit the same images in 1.0 while less time to transmit the same images in 1.1 sequential and 1.1 pipeline? Abdullah, you can comment on it.
Uh, Sir, in 1.0, every time connection is being set up, and for TCP, it's again starting from zero. That's why on each connection
Yes.
setup, the file is consuming the more time, because it's very first file for the TCP.
Yes, perfect answer. Now every one of you know the reason, because I have explained this over here. You know the way TCP operate. So the TCP starts slowly, and TCP and at the beginning the window size is small. Okay, the window size and the number of packets are the same thing. We will discuss in later lectures. So the window size or the number of packets that's small, and after that it will achieve a steady rate. Okay, at the rate which network can support. But by the time it achieves this rate, in the 1.0 the object is transmitted fully, and the server just close the connection, and the client it then send the next connection request, and then send the request for the object, and then the TCP connection, because it's a new connection, it starts again from the from the first phase, from the slow start phase, and from the window size being very low. Okay, very few number of packets sent in the early RTTs, and again when the object is retrieved, by the time it achieves a steady rate, again the connection is being terminated. But over here and over here, because after the retrieval of the first object, the connection is maintained. So the connection is already at a pretty steady rate, at a decent rate. The next objects, they can be transmitted at the same rate without going again into the slow start phase. So that's why the gray areas are shown less over here as compared to over here. Okay, so we spend a lot of time in this slide, but this was an important slide, and this slide conveys everything in this second technique. Change HTTP to make better use of the available bandwidth. Okay, that's it. We can use persistent connection, we can use pipelining, we can use parallelism. Well, parallelism is not very how do we say, not very useful in a sense that the parallel connections they start competing with each other, but persistent and pipelining, these two P's are really proven to be very useful in reducing the page load time of a particular web page. Okay, so this was our second technique. Moving on to the third technique, we can use the web caches, we can use the proxy servers, and you see an organization can decide to I'll be a bit fast. This is a much simpler technique. These slides are not like this slide, which contain many concepts in a single slide. So we all know that proxy servers can be. This is by the way, this is not the proxy servers that you guys sometimes use to to how do you say to get yourself in the incognito mode, or to visit some let's say some banned website. YouTube is being banned and you want to access YouTube, and you use the proxy server, so things like that. So this is something else. This proxy server means the organization is installing a server which will be acting as a cache. That server will be acting as an HTTP cache. Okay, so what this server will do, for instance, these are the clients in SEEX. Okay, these are the clients in one of the lab in SEEX, and there is a server in SEEX data center which is acting as a proxy server. So this server will act as an intermediate server. All the HTTP requests um, within the SEEX organization, within the users of the SEEX organization, will be directed to this proxy server. Okay, and the server will check first in its cache, do I have this content in my cache? If I have, I don't have to request to the original server. But if I don't have the content in my cache, then I will request the original server, just like the DNS server, server which has a cache. So if I have the answer, if I have the IP address of the host name, I will reply directly a non-authoritative answer. But if I don't have the IP address, I will then request the root and the TLD and the authoritative name server to get the IP address. Okay, just like that, if the server has the web object in its cache, and please note, the proxy server do not operate on a page-to-page basis. It do not cache the whole page. Rather, it caches the web objects. Okay, so we know that each web object is addressable by a separate URL. So a proxy server caches the web object. And by the way, the proxy servers, the cache HTTP caches, they can be really useful, because we have already seen in the ping dom test, and we have already seen I have already told you guys that surveys suggest that a huge percentage of the World Wide Web content is static images. So these are the static images are easily cacheable item. Okay, I mean, you cannot cache a scoreboard of a cricket match, because it's a dynamic content, because it will keep changing. Okay, there is no point in caching that content, but you can always cache static text, static tables, static images. Okay, you may not be able to so I mean the dynamic content, Java applets or scoreboards or things like that, they are not cacheable, but the static content is cacheable. So a large content can be placed in this cache, and then the next requesting user will be served with the cache, which will be a much lower response time as compared to the original server. Okay, the original server is placed somewhere around the globe, while the cache is within the organization. Okay, so the first time, if the object is not in the cache, the proxy server will request the original server. But if the object is in cache, the next time if the user asks for the same content, it will just return from the cache. So this is a much faster response, because it's coming from the same LAN, from the same organization, as compared to this, where we have the whole RTT being traversed. Okay, so what is the benefit of web caching? Well, the cache acts as both client and server. It will act as a server for the original requesting client. So, for example, this cache is server for these clients, but this cache is client for these server. Okay, so there will be a separate connection between these two, and there will be a separate connection between these two. Okay, the clients will assume that we are getting a response from this. They will request the original server. The destination IP will be of the original server, but because the organization have directed all queries to the HTTP cache, the queries will first be directed to the HTTP cache, and then the cache will request on behalf of the clients to the original server. Okay, so it acts as both client and server. Okay, typically caches are installed in university, company, ISPs, and things like that. Okay, what is the advantage of web caching? Obviously there are three advantages mentioned over here. Definitely it reduce response time for client request. Definitely, if a web object is served from the cache, if it is placed in the cache, the response time will be much lower as compared to the response time when the object is retrieved from the original server. The second advantage is that it reduces the traffic on the institutional access link. Okay, it reduces the traffic on an institutional access link. Okay, and there is a numerical to prove this particular advantage in the later slides. Okay, I will not be able to cover the numerical today. Unfortunately, I wanted to, but anyway, I will share the slides, and I really encourage you guys to have a look at the numerical, and I will skim through it in the next lecture. Okay, before moving on to the chapter 3, TCP and UDP. So there is a numerical to prove this point. Let me first discuss this point. We will see the numerical in the next week. Reduce traffic on an institutional access link. Now we know that you know after this, after the proxy server, if the request goes outside the institution, it will be using the access bandwidth. So for example, if NUST installed a proxy server, and if the requesting user from NUST, users who are in the hostels, users who are in the SEEKs, in SMME, in any other school of the NUST, if they request for a web content and they are served with the cache with the cache in the placed in the within the NUST network, then the response time will be much lower, and then also this request will not go on the access bandwidth of NUST. Okay, I hope you are understanding my point. NUST has purchased some access bandwidth from HEC, from Higher Education Commission. Okay, 800 megabit per second. PERN, Pakistan Education and Research Network, is providing us this access bandwidth. So if the request do not go, if the request is served from here, then the traffic will be reduced on the institutional access link. Okay, I hope you understand this point now. We will prove it with the help of a numerical. Okay, so these are the two advantages. One, the client will have more. One advantage is for the client. The client will have a reduced PLT. Second advantage is for the organization. The organization will have a reduced traffic on the access link, which means that the organization will need to update its bandwidth, more later. Otherwise, without cache, maybe it need to update the bandwidth every 2 years. But with cache, the organization will be able to give a better user experience to its users, and the bandwidth upgrade can be postponed. The third point is a bit tricky, but very important and very interesting. Internet dense with caches enable poor content providers to effectively deliver the content. Okay, are you getting this point? Internet dense with caches enables poor content providers to effectively deliver the content, and this term poor here is really used in the literal meaning. Poor means poor. Okay, poor means the content providers who are actually poor. YouTube is not a poor content provider. Okay, right? Amazon is not a poor content provider. Okay, eBay and Facebook and Twitter, they are not poor content providers. They can afford to go to this option, CDNs. Okay, what they can do is that they don't need caches installed in organization, university. They don't need the support of ISPs to install caches, because they are rich content providers. They having a plethora of users and very huge network and very huge footprint. So they can pay Google or Akamai or Limelight that this is my content, and please disperse this content across the globe in your data center so that my content move closer to the client. Okay, but this is something different. This is not moving the content closer to the client. This means that the content is being cached locally with the help of a cache, a cache server, a proxy server installed by the ISP or company or university. Okay, and this will help the poor content provider. So let's say there is a there is you guys want to share some content, and I mean we can say what example. I mean, there is some personal website. Okay? You create your personal website, and if that website has many images, then and those images are being cached around the globe in the caches, and then people around the globe want to visit www.arsalanahmed.com. They will have a better experience, because I cannot afford to pay Akamai or Limelight to disperse my content in their nodes, in their data center around the globe. So I am a poor content provider, but I want my content to be effectively delivered to the user. So if the internet is dense with caches, if every ISP around the globe, every university, every company installed their caches, I will have a very good advantage. Okay, what I will have is that my content, when it is requested for the first time, only at that time there will be more PLT. But after that, if there are more users requesting for the same content, then the users will be getting much of the web objects from the cache which is very near to them, as compared to the original server which I am hosting here in Islamabad, let's say. Okay, I hope you understand this point. Okay, so web caching has all these advantages. Okay, and how web caching work? This is the last slide. We'll conclude. After that, there is a numerical. I will this numerical. I am going to leave it for the next time to discuss. So how web caching work? You know, we have. By the way, the level of caching is different. We can have a cache in the browser as well. So even if I mean, there is a cache in our organization, and there is a cache within the browser as well. So few of the content is cached inside the browser as well. Okay. Okay, right now there is a very important question. When is it okay to use the local copy? Okay, I'm just going to finish with this question. When is it okay to use the local copy? Because it is quite possible that the copy that you have in your cache right here or right here, okay, that copy is stale. Stale means it's an old one. It has been modified. Okay, so what we can do, we can use these heuristic, sorry, not heuristics. We can use these heuristics, or we can have the conditional get statement. Okay, we can have the conditional get statement. So, for example, if you request, I postpone the discussion of heuristics. Okay, it's something related to the algorithms. I postponed this discussion because it's 5:53 right now, and we lose the opportunity to conclude the topic. Okay, I mean, excluding the numerical. I want to conclude the topic excluding this numerical question which is coming over here. Okay, so uh, we will uh, um, we will um, we will use the conditional get statement, and so the requesting server will request the cache. The cache is acting as a proxy, and the cache will check, okay, I have a copy of the same web object, but is my copy valid? Okay, to validate my copy, let me send a conditional get statement. It's different from the get statement. A conditional get statement is the one in which I ask the original web server that this is the version that I have. Okay, the image, the table, the CSS style sheet, whatever. This is the version that I have. Okay, I will send a last modified date, and this is the version that I have, and the conditional get statement will be received by the web server, and the web server will check, and it can give two possible responses. One response can be that it is not modified, the copy that you have is a fresh one, and the other response can be no, that's a stale copy, and please have this fresh copy. Okay, and the data will be in the message part of the HTTP response. Okay, so it's shown over here as well. Okay, I'll conclude at this slide. So just final remarks. So if modified since the date, okay, HTTP request message, and the response is there can be two responses: 304 not modified, which means the copy that you have is the one that I have. It's not stale. It is freshly validated. Or the other response can be HTTP to 200 OK, and then there will be data coming with this response. Now, one question comes, the last point of the lecture. I want to ask you guys that if we still have to send a conditional get statement, then what is the advantage of this proxy cache? I mean, why do we need this proxy cache within our network if we even after having the copy of the content, we are still requesting the web server? So what is the point? What will be the benefit? Anyone?
Sir,
Anyone who is awake and listening?
Sir, I think it will just be for a certain amount of time until the expiry of the content in the cache, and then it can check whether it was modified or not.
Okay, so yes, you are right. Correct answer, and I will build up on that answer. That further that one point you are absolutely right that if the copy is freshly validated, okay, and it is a cacheable item, it's a static item. Now comes the heuristic part. It's a cacheable item and it is freshly validated. I have just recently asked the original server that this copy is not stale. Then I will just respond from my cache. And the second thing as well, even if I am asking the server, the not modified response will be just few bytes because it do not contain the data with it. Okay, so this response is just few bytes. Okay, because the server is just responding that yes, the if modified date that you mentioned is the one that I have in my backend database, and you don't have to worry, and you can give the copy that you have at your local end. Okay, so this response is much easy on the network as compared to this response. In this response, we are getting the data as well. So even in the conditional get scenario, we are still having a tactical advantage by installing the cache at our end. Okay. Okay, I will conclude at this point. The numerical we will do at the start of the next lecture. Is there any question? We will take question in the next at the beginning of the next lecture. But the silence means that there is no question. Let me stop recording also.